Now, what I want to do is we've spent a little time explaining how change of basis work, and we're going to come back to the example of principal components analysis, and in particular this first example, well, the second example, but the simple example that I wanted to start with, which is the height and weight of hockey players. So I'll remind you that there's a link here to a Stack Exchange page which has some data sets on weight and height, and this is one that I picked. So as always, you would get the data from the web, for instance. Unless I distribute a file, then it's best for you to actually download the file this way. And you'll see it will take a little time for this to happen, but after a while, we get a data frame that has 13 columns. So the year in which the competition took place, the country from which the player hailed, the number of a player, the name, their position, their side, etc. And here we're actually going to look only at these two columns, which are going to be the height and the weight. And in total, we have a large data set. This thing did not appear, but yes, there it is. You can see we've got 6,292 individual records, but as I mentioned in a past discussion on this data set, what happens is that some of these players, of course, played repeated times in those championships, and therefore it is because we're going to focus on individual players, it needs a little bit of sorting things out. So if we plot the result, we get this plot, which has so the height and the weight, and so you can think of weight as a function of height, or it's just a two-dimensional plot. And here, the person who wrote the problem was interested in the evolution of the weights, and so we're going to disregard this. So what we're going to do is we're going to take individual players and compute a mean weight and a mean height. And so I'll just point out that what is happening is that you have a certain number only of individual names. Okay, so remember there's 6,000 something records, but that corresponds to 3,300 essentially individual people, and that's what we're going to look at. To do that, and I mean, it's important not only to understand the math, but to understand how you can play around with the data. So here I'm giving you another example of manipulation of data. What I'm going to do is I'm simply going to take, for each individual player, potentially the mean height and mean weight that they have in the database. So for this, I create a new data frame that is just going to have, for the moment, the names, and I'm preparing two vectors, W and H, that I'm going to add together with these names, and that are just going to be the mean weight and the mean height. And so what I'm doing here is I'm simply taking each individual name. So just as a remark, and we've seen that a couple of times already, I'll point out that we could also go for indices in the data frame. Okay, we could go from I is 1 to the dimension of the data frame. But here what I'm choosing to do is, instead of picking individual rows, I'm picking individual names. Okay, so I'm going down the names, and what I'm doing is I'm selecting in the original data set the rows that correspond to the name that I've chosen. So if for example, I were in that data set, which of course I never would be, at one point I would say select all the records that have Julien Arinault, and this temp matrix would contain all the rows in my original data that have this name. And then all I do is I simply add to these vectors that were initially empty, I add to them the mean height and mean weight that I've computed. Once I have that, I have a mean height and a mean weight for each individual player. And I add this to the database, well, to the table, by saying that the height and the weight are these values that I just computed. And after that, what I do is I go back to calling data, this new data set. Okay, I'm forgetting all of this information that I had before. I'm just keeping the names and the mean height and mean weight. Okay. So when I do this, I end up with a table that is going to have 3,278 rows, and for each person is going to have a weight and a height. When I plot this, I get the following result. You can see that there's a little less, let's say, crowdedness here below than there is here, because what is happening is that your we've taken out about half of the data essentially. Okay. So we get something that is more concentrated. And these are the points that we are going to look at. Now, the first really important step to take whenever you're doing your PCA is the one that we do now. So if you look at this data set, you can see that it is varying from 170 to 2 something and 70 to 120 or so. What I'm going to do is I'm going to center this data around the mean. Okay, so now I have my data varying around the mean height and the mean weight. So now I'm expressing things in terms of variation around 0, 0. 0, 0 is the mean height and the mean weight of my data set. And variations around this is what I'm looking at. And by the way, so if I plot the mean, well, if I represent the mean weight and height, I get these values. So all these players that we have, in total, their mean weight is around 88 kilo and the mean height is around 1.84 meters. Now, I can use the function covariance. Remember, I mean, so now you have to go back a couple of lectures ago, but remember that the covariance studies how a sample, how data in a sample varies with respect to other data points. So I can use the function covariance in R to compute the covariance of two samples. And here we have height and weight. So we can look at this. Okay. Just a remark in passing. So covariance works whether you're centered or not. And you can see this by looking at this here. Okay. I'm computing, by the way, yeah, I didn't mention this is the height centered. The dot C is for centered, and this is the uncentered one, and we get the same value. Okay, but if you recall, well, you'll recall that the covariance matrix we can just get the same way by looking at this matrix here. Okay, so this is, I'm going to take the matrix X to be the data matrix with the centered heights and weights, and then I'm going to compute 1 over n minus 1. So n minus 1 here is the dimension of this matrix X times the matrix product of X transpose times X. And if you recall, we saw that this was an unbiased estimator of the covariance matrix. And you can see that what we get here, and I'll just point out that the values we get are exactly the same, essentially the same as the ones we get when we look at the covariance. So here, 26.6305. Remember, the covariance matrix is a symmetric matrix, and these 26.63506 is essentially what we get here. Okay, and the off-diagonal entries are the covariances, but we also see that the variances work the same way. You can see that here I get the variance of the first sample, so the height, and here the variance of the second variable, the weight. Okay. Now, let's look at the second step. If you remember, for the PCA, what we have to do now is look at this covariance matrix and compute its eigenvalue decomposition. Okay, so we need the eigenvalues and eigenvectors, and then we're going to take the the square roots of the eigenvalues. So first we use the function eigen to find the eigenvalues, and we find these two eigenvalues. The largest is 66, the second is 10, and the corresponding eigenvectors are, this one corresponds to 66, and this one corresponds to 10. Okay. I'll just mention that when you call this function eigen, you're going to get a bunch of eigenvalues and a bunch of eigenvectors, and the corresponding eigenvectors. There's no reason a priori for things to turn out as they did here, which is what we want. You recall that when we're looking for singular values, we want them ordered by decreasing values. So there's no reason for this to happen. And so it's good to actually proceed as we do here. So I'll get an ordering of the eigenvalues, a decreasing ordering of the eigenvalues, and I'm going to apply this to both the eigenvalues and the eigenvectors. This way I have, after doing this, I have my eigenvalues in decreasing order, and my eigenvectors are ordered the same way as the eigenvalues. So, well, here it doesn't change anything because we had the right ordering already, but it could happen that things don't work out that way, and still we will be good. Another remark is what we are getting out of this procedure is also normalized. This doesn't have to be the case. So the same way as we normalized the eigenvalues and eigenvectors, the same way as we ordered the eigenvalues, let us normalize the eigenvectors. And I'm just going to work with the first singular value here. Okay, so this is just the one that I'm going to look at. So I'm just going to look at the first eigenvector, and I just normalize that eigenvector by dividing it by the square root of the sum of the squares, okay, so by its norm. So I do get this, and my vector indeed has norm 1. I am good. Now let's plot this eigenvector. We're not plotting the eigenvector just by itself, we're actually plotting the entire line. So to do this, I am going to use AB line that we've used already, and AB line needs, I mean, if you'll recall, we can call it several different ways. One way we can do is by the slope intercept. And I'll remind you that here, because we've centered things and that we're dealing with an eigenvector, that eigenvector of course goes through 0, 0. So in terms of slope intercept, my intercept is 0. And all I need to look at is my slope. And my slope is obtained by just looking at this quantity here, which is giving you the angle, essentially, of the eigenvector. Okay, so when I plot the two together, the data and the eigenvector, you can see that this is making sense. Remember that what we are doing when we're computing the principal component analysis and the principal components, so the singular values, we're trying to get the main directions in which the data is changing. Okay, so this is concentrating the most variation around this axis here. And I'll just point out that this is a little tricky to look at. I should have made sure that the axes were square, because this is slightly misleading, because from here you have 40 values, here you have 50, so there's more dispersion that way. Now I want to take the opportunity to show you something else, which is how to use a native function in R, which is very, very useful, because in linear regression is used a lot in stats, and that's why this function is here. So here I'm using, I just want to show you two different versions of looking at the data this way. Okay, so the function linear models is a very standard function in R, and you can use it to run a linear regression. It's a linear least squares problem. So here what I'm saying by doing the call that I have here is I'm saying Z is the linear model, so it's the least squares problem, where I'm looking for a line. Otherwise I would have squares in here. Okay, I'm looking for a line that expresses the weight, and remember dot C means it's centered. It's the data that I've centered. It expresses the weight as a function of so this here on the right says y is equal to a being 0 plus bx. Okay, so here b is going to be my parameter and x is the height. So I'm looking for a linear least squares fit to this data. Okay. As I said, I'll hand out this code so you can take a look at it. When you look at the result of Z, it contains some information. It tells you what function you used and what coefficient you got. And this is here the angle that we get. And I'll just point out, so here I'm plotting as before the direction of the dominant with the largest eigenvector, the eigenvector associated to the largest eigenvalue, so the largest singular value, it's still in red. And this here, this green line is the one we get by doing the least squares fitting. And it's normal that they don't look exactly the same. Sometimes they will, but because they don't exactly minimize the same thing, and the least squares is minimizing the distance between the square of the distance between the points in the green line, whereas the red line comes from computing the from computing the eigenvector corresponding to the largest singular value. Just to show you what we could do, we can take this data, and if we rotate things around the red line, things will be easier to see. Okay, and there's a type of matrix that I may have mentioned, but that you might have seen actually in first year when you were looking at linear transformations, which is called a rotation matrix. And here I'm going to compute the rotation matrix that is needed to make this data rotate. So to do that, it's quite simple. So rotation matrix is simply defined this way. So if theta is an angle in radians, typically, then the rotation matrix that rotates all vectors. So here you have to think of each of these dots as being the endpoint of a vector. Okay, because if you think about it, it doesn't really make sense to rotate a point. But what you're rotating is the vector itself, with the point being the endpoint of the vector. Okay, so that matrix that has this expression here rotates all the vectors by an angle theta. And to find this angle, well, we just need the angle of that red line. And this we get by using the fact that this angle is equal to the tangent of one dimension versus the other, one direction versus the other. Okay, so we compute the arctangent of this angle, and that gives us the theta that we use in the matrix. Okay, and this is what I do here. You can see that the angle is 0.94, so it's a little underneath pi over 2. So we need to rotate by a bit under pi over 2. We need to rotate by this angle in radians to make this red line horizontal. Okay, this is our aim here. And the matrix that performs this rotation is then this matrix R theta. Now, to do this rotation, I have to take each point or each vector in my data set and apply a rotation to it. Okay, so this is what I do here. I'm simply making a matrix that has the centered weight and height, and I'm applying the rotation to this matrix. Okay. When I do that, I get this plot here, which looks not as good, but I'll point out something. What we've done by rotating things this way is that we've made this axis way less wide, if you want. The range is much thinner than it used to be, because when I was looking at the data here, the data ranged from -25 to 30, whereas here you can see the data ranges from almost 20 to 15. Okay, so if I normalize, well, not normalize, but if I plot in the same axes than I had before, you can see that what we get is something which is much more resemblant to the data we had before, except that now, if I were to plot my red line, it would be horizontal. Okay. And the last thing I want to do, I don't want to spend too much time on PCA in this particular context, because as I pointed out already, PCA here doesn't mean a lot, because we've only got two variables that we're looking at. And it's when we look at the full-blown examples later that we'll see much more value to the method. But let's look at how we could do things properly. Now, the one thing I will point out is there's a function called pragma, and I should move this here. So if you haven't, I mean, when you're running this, you get an error. It means the pragma package is not installed. I should move this actually below this. It means the pragma package is not installed or library. And so what you need to do is install it, which is what I'm doing here. But I've installed it already, so I don't need to do it. You can see what the function here says, and you probably wish you had it before. Well, there's a function to compute the Gram-Schmidt, to apply the Gram-Schmidt procedure to some vectors. And here, the input to this function, we're using the eigenvectors we have. Okay, so when we run this, we get, probably I should show you what we get. So you can see when I'm doing Gram-Schmidt, I get a matrix Q and a matrix R that are essentially the result of using Gram-Schmidt on this, and where the matrix Q is the, in the QR decomposition, the orthogonal matrix, okay? Now, here, what we are now going to do is we're going to apply this Q to make the new basis in which we are going to express the data. Okay. So what I'm doing here is I'm making a matrix A, but it's simply the matrix Q. Okay. And so what you get in fine, I'll explain in much more detail when we get to the proper example, okay? But so our matrix A is this matrix here. And what I'm doing is to find, so if you remember the change of basis matrix, we can get by setting up the matrix in terms of the matrix Q here, with the matrix of change of basis here, and sorry, not the matrix of change of basis, the vectors in the new basis here, and the identity here, and then looking at the reduced row echelon form, we now get the matrix of change of basis in the right. So this is what I'm doing, but I'll point out that I'm just selecting here the third and fourth column, because what I know is that when I look at the reduced row echelon form, let me add this perhaps, the reduced row echelon form of this matrix A. So A is this matrix here, and so what I get after reducing this matrix to row echelon form is that here I get this matrix P, the matrix of change of basis, and here I get identity. And let's check that this is indeed the case. Of course, I did not load the package. Why? Ah, yes, because I did not. So that's a remark in passing. So this is a perfect illustration of something that happens from time to time. When you use pragma two columns this way, what you're saying is go in the library pragma and find the function reduce row echelon form of A. Okay. Otherwise, what I could say is load the library pragma. But here, I'm not interested in loading the entire library. I just want to use that function and actually the Gram-Schmidt function. And so what I can do is I can say pragma like this. And this simply means use that function in pragma. But because I haven't loaded the library yet, that's why we get the problem. And indeed, as I was saying, we start out with this matrix and we finish with this matrix, where this is identity and this is the matrix of change of basis that we then use to recast our data in terms of the first two, in this case, the only two singular values. And that's it for this, I think. And so, as I said, you'll see a much more complete example when we look at higher dimensional data.